This is the second part to lesson 1.2. We're going to do 4 examples talking about dependent variables, independent variables, and functions, just to help you understand functions better. So example 1a, in a right triangle, the sum of the measures of the two acute angles is 90 degrees. So you have x and y equaling 90 degrees. Suppose x is the degree measure of one acute angle and y is the degree measure of the other, as shown in that drawing at the right. You can write an algebraic sentence to describe the situation, and we talked about this in the last lesson. X plus y equals 90. And that algebraic sentence has the equal sign and is showing that x plus y equals 90. Now you can subtract x from both sides of this equation to get y alone on one side. So in this equation, which of x or y is the dependent variable and which is the independent variable? Explain your answer. Well, in this, we can look at and we can go y. We can say y is the dependent variable. Because we need to know x to get y. So the only way we're going to solve for y, in other words, is if we have x. So y is dependent, it's depending on x. And that makes x the independent variable. In example 1b, two angles of an isosceles triangle have the same measure x. So here, two angles of the same measure x. The measure of the third angle is y. This relationship can be modeled by the equation y equals 180 minus 2x. Which of x or y is the dependent variable and which is the independent variable? So they're saying the equation y equals 180 minus 2x. Which one is going to be dependent and which one is going to be independent? Well, if you look at this, you have y equals something, so we need to know that something before we can solve for y. The only way we can get y is if we get x. So that makes y depending or dependent. It's the dependent variable. It's depending on x. And x becomes the independent variable. Okay, example 2a. The percentage P of the adult U.S. population aged 25 and over who have earned a 4-year college degree by the year Y is given in this table. So now we're going to talk about functions. So is y a function of P, y or y not? So what was our definition of functions? We said that a function was a relation where no two ordered pairs have the same first component. We also said it was like a machine. If you put in one number, it transforms itself into another number based on a rule. So is y a function of P, y or y not? Well, let's look at our values. For each value of P, there should be only one value of y. So we should have, for every value of P, there should only be one value of y. If we look at our p's and our y's, y cannot be a function of P. So y is not because if you look at P at 21, that 21% here and there, it's paired with two different years. And we said for every input that's the same, it must have the same output. So these 21s should have the same output, and they don't. So y is not a function of P. So let's look at part B. Is P a function of y? Well, look at every P. For every P, and then look at our y's. P is a function of y because each year is paired with only one value of P. So P is a function of y because So P is a function of Y because each year Y is paired with only one value of P. Let's do another example on that. Thinking about functions can be a little confusing. So example 2b. The average annual price P of crude oil per barrel in the year Y is given in the following table. So that's this table over here. Is Y a function of P, Y, or Y not? Well, if we look at the table, Y is not a function of P because if you see P at $16.75, that's the same. That same input has two different outputs. So Y cannot be a function of P. Is P a function of Y? Y or Y not? P definitely is a function of Y because each year, so each Y, is paired with only one value of P. So P is a function of Y.